The next thing I wanted to talk about is what's called the Fundamental Theorem of Calculus. Sounds very important, and it really is, but it's essentially wrapping up into a nice bow every idea that we've been talking about in the last week. And I think it's quite important because it kind of emphasizes the connections that it has been developing and going through. But let's just look at it. It says, if a continuous function f has an antiderivative, capital F, as is normal with the notation we use, over an interval AB, then the limit as n approaches infinity, which again, as you remember, this is the formula for a Riemann sum with n subintervals, meaning if I take an infinite number of subintervals of a Riemann sum, adding up all the area under the curve, basically this is the exact area under a function over a particular interval. What it says is this, the Riemann sum, the infinite Riemann sum, is equal to the definite integral of f of x with respect to x. Again, kind of as I was saying in the last video and in class, this sort of morphs into the integral symbol. This turns into dx, as in the way we define a definite integral in the representation. But those are equal to one another. And thirdly, the definite integral of f of x with respect to x over ab is equal to the antiderivative of f evaluated b minus antiderivative of f over f of a. So essentially, and putting this below, translating this to more of the idea, the exact area under a function over an interval is always equal to the definite integral of that function. And that is always equal to the antiderivative of that function evaluated at b minus a. So there's a connection between these mathematical expressions, which was proved in tiny parts. And also, remember what a theorem means in mathematics is something that is true. We can prove that this is always true, and that's why, of course, it's very useful. As we've been looking at in the past few examples, we've been solving area using this idea, which is way, way easier than trying to think about Riemann sums and adding up a bunch of rectangles. But it's conclusive proof of this. In most textbooks, I would say, don't even get into, well, why? This is a question like, why is the Riemann sum? Why does it equal this? But the theorem has been known for quite some time, and the proof of it is quite complicated when the book doesn't even really get into it. Except for into certain cases. But yeah, again, kind of as we've been talking about, area function is the antiderivative function, and if we use the referential points to take the difference of those, we can get the area under the curve. And thinking about this in terms of derivatives and antiderivatives, if we're just thinking about a function and what it does, if we were to take the derivative of a function, like just say d dx, that is what we call a slope function, because the derivative gives us the slope at any point in time. We can find the slope of a tangent line, blah, blah, blah. F prime of x is the derivative operation. And so, sometimes we refer to an antiderivative as an area function, antiderivative of f of x with respect to x, or capital F, if we're calling this one f of x. And, we call the derivative f prime of x, just like we use ddx. And the integral symbol is kind of like with respect to x is the Leibniz notation. And if we're using function notation, capital F is common. There is no prime for an antiderivative. And then, but also in the same way, thinking about derivatives and antiderivatives, well, if you took the derivative of an area function, it would return you back to the original function. So if you take capital F prime, that's equal to F by, that basic idea. And similarly, if you take the antiderivative of a slope function, it will return you to the original function. And all these ideas are quite useful because sometimes in business, we know the rate at which something is changing, but we want to know what's the original. So you can always take the antiderivative of a rate function to return to the primary relationship that we want to study. And antiderivatives can be used for a lot of things such as that. So applying the fundamental theorem of calculus, once again, say we wanted to find the area underneath the graph of 1 over x squared from 1 to 10. And, here we have a graph, which is actually not very well done. This should actually be quite a bit less steep if it were properly designed, but that's okay. It gives us the idea of the shape. But basically, if we want to find the area under the curve, we can always set it up as a definite integral. And this is kind of like the first part, is instead of doing the Riemann sum, we just take the integral from 1 to 10 of f of x with respect to x. And then we also know how to solve this by applying the antiderivative and plugging in the boundary point. So if I'm thinking about, well, 1 over x squared, that's the same as x to the negative 2 power. The antiderivative, I could use the power rule to find that by adding 1, x to the minus 1, and dropping the reciprocal, so dividing by negative 1. And I don't need plus c again whenever those little numbers are there. We do not need plus c. And then can't forget that I also need to plug in my boundary points, 10 and 1, starting on the top. So this would just be, well, again, I could even simplify this and just write this as negative 1 over x from 10 to 1. And then I can plug them in. So this would be negative 1/10 minus. Also, remember, be careful with your negatives when you're doing definite integrals, because remember, it's always the first one minus the second one. So I like to put them in brackets so that if I have a negative, I'm going to remember a negative there. And then I need to take away the bottom, again, which is another negative, leaving me with a double negative. So really, this would be negative 1/10 plus 1. And 1 minus 1/10 is exactly 0.9 to give me the precise area under the curve over this region. Additionally, let's say we wanted to do the same problem but over a different interval. Let's say we wanted to take this from 2 to 5 instead, and check out a different segment of the area under the curve. Well, it would be the exact same process. No matter what, if we know the antiderivative function, that's what matters most of all. And I could do some shortcuts now that I've already run through the math for this function. The more antiderivatives we know, the easier it will be for us to find the area of different curves. So, right away, I know the antiderivative of this is negative 1 over x. I'm just changing my boundaries of integration from 1 to 10 to 2 to 5. And then this will just change the math. Well, I'm going to have negative 1/5 plus 1/2. And that would be 5/10 minus 2/10. So this would be 3/10 or 0.3. And it's just going to give me a different amount of area based on the change in the interval. Also with negatives, same deal. You can use negatives, but there are particular issues that you need to be careful about. Is certain functions, like notice 1 over x squared has a discontinuity at 0, right? We might say it's undefined at 0, or 0 is not within the domain of this particular function. So, and if we were to look at the graph of what 1 over x squared looks like, it looks something like this, where it has a vertical asymptote or basically there's a discontinuity in this function. If you remember, whenever there's a discontinuity or a missing limit in a function, like at this one occurs at 0, it is not differentiable, and in the same way, it has no antiderivative as well. So if we were to try to solve the under the curve, like say you were given an interval such as this, and I was just to set it up, negative 1 to 1 of 1 over x squared dx. This is technically not allowed because of the discontinuity within that interval. Integrals are not defined at a discontinuity. If you pay very close attention to the fundamental theorem, it says if a continuous function f is continuous on that interval, then it works. So just a thing to note. And that's one of the reasons we care about discontinuity, because integrals will not work over those intervals. You can even try typing them in your calculator. Sometimes it will actually give you answers incorrectly, and actually there is a way to solve such integrals. Technically, you can figure them out. It's a little bit more complicated, something that we would typically talk about in a Calculus 2 course.